Hello and welcome back. These would be some additional examples for Chapter 7, Section 1, Solving Systems by Graphing. There is a PDF available if you'd like to print it out and follow along. First thing we need to do is graph our two equations. They're both in slope-intercept form, so it makes the graphing of them pretty easy. So I'm going to graph the first one here, which has a y-intercept of 6. So I'm going to put my dot at 6, or try to put it at 6. And it has a -1 slope, so that means down 1 over 1 to the right. So I'm going to go down 6 and over 6, which is still -1. Now I might have to make my line longer, depends on where my other line is. Now the second one has a y-intercept of -2 and a slope of +1. So put my first dot at -2, which is right about here, and up 1 over 1, so I'm going to go up, see, 5 and over 5, right about there. And graphing is not always the most accurate measurement for a system, but it appears that the solution system is right there where the two lines have crossed each other. The question is, what are the coordinates at that point? The coordinates there would be 4 and 2, 4 and 2. And the only way to be absolutely certain would be to substitute a 4 and 2 in place of x and y in both equations. We're going to try that out here real quick. So this would be 2 equals a -4 plus 6, and a 2 is equal to 4 minus 2. The top one checks out and the bottom one checks out. So this is the solution of the system. For this next example, we have two equations that are written in a standard form. So I can either use the x and y intercepts, or I can use one of the intercepts along with the slope of the line. The first thing I'll notice is my y-intercept here on the first one is 7. That's right about here. I don't like this particular graph because it's going by 2, so my lines aren't going to be all that accurate when I go to draw them or graph them. So it's more important to check my solution on a graph like this than it is at any other time. Now my x-intercept will end up being 7 over 3, which is not a very good point to graph, so I'm going to go ahead and use my slope of the line. The slope of the line is going to be the opposite of 3 over the 1 out in front of the y, so it's a -3. So in order to calculate this, I got to go down 3 and I got to go over 1. So down 3, that would be 1 right here, 2 right there, 3 right there, and then over 1. And then I can go down 1, 2, 3, and over 1 again right about there. Now again, I'm just eyeballing this because my points are approximately halfway in between. That one doesn't look very close to halfway. Let me change it a little bit. There we go. Right about there. And then the next one, next equation, I have a y-intercept of the -8. However, my graph does not go low enough for that. So I'm going to check my x-intercept. Well, my x-intercept is going to equal the -8 over the -2. That's going to give me a +4. And that I can actually graph on here. +4 should be right about there. And the slope of my line is going to be the opposite of the 2, the opposite of this 2 here, over the 1 out in front of y. So I have a slope of 2, but the intersection is occurring in this direction. So instead of going up and to the right 2, I'm going to go down 2 and to the left 1, right about there. And you can see the intersection appears to occur at an x value right about here, an x value. It looks like it's about a 3. And the y value appears to be a -2. But since this graph does not go by ones, I'm going to have to go back and double check my answer, make sure that's actually my solution. So in the first one, I have 3 times 3 plus a -2. Does it give me 7? Well, that's 9 plus -2, so yeah, it does work in the first one. And the next one is a -2 times 3, and I'm going to add a -2 to that one. And next question is, does it equal -8? Well, that would be a -6 plus a -2, so it does equal -8, and it checks out in this one. Therefore, this one is my solution. Next question, or next example here, is the point a solution of the linear system? Well, the only way to know is to substitute just like we did in the last example. So we're going to do 5 times x, which is negative 2, minus 2 times 1, and check to see that that equals negative 12. And the same thing down on the bottom, we're going to do a negative 2 plus 3 times 1, and check to see that that equals positive 1. So the top one is going to give me 10 minus 2 equals, actually it's a negative 10, minus 2 equals negative 12. It does check in the first one, therefore we have to check the second one. So I have a negative 2 plus, change that, negative 2 plus 3, and that equals a positive 1. So it does check out here, so the answer is yes, it is a solution. Another one, is this point a solution of the system? Well, we got to go ahead and check and see. So in place of x, I'm going to put a negative 4 plus 3, and in place of y, I'm going to put a 3 equals negative 12. And here we have negative 16 plus 6, and actually that's not 6. So we have a negative 16 plus 9 equals negative 12. Well, negative 16 plus 9 is negative 7. And does that equal negative 12? No, it does not. Since the point does not check out in the first equation, there is really no point in trying it in the second equation. It could work, it couldn't work. It doesn't really matter. The answer here is no, it is not a solution. As soon as you find one equation that doesn't work in, it's not a solution to the system. The last thing we're going to look at here is how many solutions does a system have. What we're talking about is a dependent, independent, or an inconsistent system. The way we tell is if we have two different slopes, you're guaranteed to have one solution. What that means is you have two intersecting lines. If you have the same slopes and y-intercepts, that means they're both the same, you end up having the exact same line, which produces infinite solutions. However, if you have two slopes that are the same, but the y-intercepts are different, what you have are lines that are parallel to each other, which creates no solutions. So here we go. We're going to check each of these systems, see what kind they are. So the first thing I always want to check is to see what the slope of the equation is. So the first one here is a negative 2 over negative 3, which is a 2/3 slope. And the bottom one is a negative 3 over 1. So we can clearly see that the slopes here are different. Therefore, this system has one solution. That means it's an independent system. The next one here will be a negative 8 over a negative 12, which is positive, and this will be a negative 2 over a negative 3, which is also positive. And then we're going to go ahead and simplify the top ones. We want to compare negative 8/12 to 2/3. So we'll go ahead and divide by 4, and we end up with a 2 over 3, and this is a 2 over 3. So right now we can see that the lines have the same slope. Well, we can see that there's two kinds of systems that have the same slope. One is infinite solutions and one is no solutions. So what's the only difference between them? One has different y-intercepts and the other one has the same y-intercepts. So we got to check and see what the y-intercepts are. Okay, so over here we have the top one has a y-intercept of 16 over negative 2, and the bottom one has a y-intercept of 4 over negative 3. So if I reduce the top one, see if it is equal to the bottom one, and divide by 4, I end up with a 4 over negative 3, and we can clearly see that the intercepts are the same. Therefore, these are exactly the same lines, which produce infinite solutions. The last one has one line in slope-intercept, which is always easy to tell. There's my slope, there's my y-intercept. The second one is actually in standard form, so I'm going to go ahead and calculate my slope there, which is the negative 8 over negative 2, which is positive 4. So you can see right now we have the same slope. The only question is, what's the y-intercept? This one is a negative 7. This one's going to be a 12 over negative 2, which is negative 6. They have different intercepts, which means they are parallel lines, so there are no solutions.